Okay, so welcome everybody for the last week of the summer school. So this week we'll look at computational perspective. So we'll have 3 days. So today we'll speak about logic and ontology. Tomorrow it will be about neural interface, and finally on Wednesday, satisfiability. So the talk of today, we'll have Ian at first, who will speak about natural languages inference from Aristotle to AI. Then Uli, who's at the distance on Zoom, who will speak from word embedding to ontology embeddings, preserving meaning in space. And then this afternoon, we start with John on Zoom again on logic for ontologists. And finally, we'll finish the day with Dean on trust semantics, large language model, using knowledge graph as a countable sort of truth. Okay. So maybe to some sort of pinpoint the setting of the kind of talk that you will have today. So logic, not something new for those who were there last week. So there were already many talks on logic, but this week we'll look really at logic from a computational perspective. So logic is the science of reasoning, and we'll specifically look at languages to express knowledge. So you can express knowledge like the ISC 9000 is a course. You can express it symbolically. So you have this kind of expression, and also relationship between things like Roger's enroll in the ISC 9000. So enroll in is a binary relation between two things, between Roger and between the ISC 9000. So you have languages to formally express knowledge. And another central thing is that you have method to infer implicit knowledge from actions, so from general knowledge that you can use to infer implicit facts and knowledge. So like here you have an expression and description logic that you don't have to know the details of the syntax, but if somebody is enrolled in a course, then it's a student. So you express it formally that way. And now with this general knowledge, you can infer that Roger is a student. Why? Because you know that IC 9000 is a course. You know that Roger is enrolled in this course, and you know that anybody that enrolled in the course is a student. So you can infer that Roger is a student. So it's an implicit knowledge that you can infer in some automatic way. So what's important is that inference can be formally processed. It's similar to what you have in arithmetic. If you have some sort of computation, you can just compute and get the answer. And similarly here, you can process these expressions symbolically at hand or with algorithms to really check that it's an inference. Of course, there's some limit to what you can do with computation, is that you can check that an inference is correct. So if you give me an inference, I can check every step to see if it's correct. Exactly like if you give me a computation, I can check every step of your computation to see that it's correct. So you have algorithms to do that. But you don't, in general, have an algorithm that can tell you is there or not an inference of some fact from some general knowledge. You don't have an algorithm to do that in the general case. But if you restrict the kind of logical construct that you have, you restrict the kind of thing that you're able to express, then you may have, in specific case, algorithms to do that. And then when you have an algorithm, then it can be more or less complex. So it has a cost in terms of time and space. So how much time does it take to process these facts to see if there's an inference or not? And also that the space that's used for the computation, the quantity of memory that the algorithm will use, that can greatly vary. So Ian will tell us more about these kind of things. And of course, today there will be a lot of relationship with large language models, something that you probably heard a lot about. And so you can ask yourself, so isn't already the case that large language models just solve all these problems because you can ask a question, you'll get an answer. But in fact, it's interesting to reflect on how these models work. And the crucial fact is that the LLM will predict next word using parameters. So you have thousands of parameters and they are adjusted based on data in a training on the large corpora. So you have a large amount of text that are processed, and then these parameters are adjusted. And you also have further training on question answer when you want to have a model that will be able to answer question. So after training, LLM can be used to produce answer, and it produced answer one word at a time. So using these parameters, what you have is that you have an approximation of what are the probability of the next word, and you produce the text in this way. So you have implicit result, as you know, but in fact, you have no absolute guarantee. So it will produce a text that looks like a text, but otherwise you can ask yourself also, why do you have these so-called hallucination, which are things that are not true, but it's only because it's not really a problem, because what you have is a process to generate text. So generating text that looks like a text, but what it's expressing is not necessarily right. So it's not, there's no guarantee that it will get things right. Even the syntax and the correctness of the sentence, it's not completely guaranteed, but it's only that usually it works pretty well and get pretty good result. So of course, an important question today is that with LLM, you have a high-speed response, so you can really rapidly get, after the training is finished, so the training is long, but after the training is finished, you can rapidly get response. And you can ask yourself, is it possible to combine that with logic accuracy, where you express facts and you have methods to check inference? So of course, today there will be a lot of facts and results around that. So this is a really important research topic nowadays. Okay. So how does the LLM works? It's so one general, maybe important fact is the fact that it uses embeddings to represent data by vectors. So everything is represented by a sequence of real numbers. And so when you have these words, they're represented by these vectors, and this is how it's processed algorithmically. So if you represent similar notion by similar vector, then usually it will make the training easier and you will have better performance. Maybe the general idea is that if you have Monday will be mapped to some vector, Tuesday will be mapped to another vector. If the two vectors are near, then it's easier to answer question like, is Monday a work day or is Tuesday the work day? So if the words that are here are near, then it's easier to some sort of trigger the same response, which would be yes in this case. So the general idea is that if things that are related are not far away as vector, then it should be easier to do the training and it should be easier to get good result. And that's experimentally demonstrate that it works. Okay. But now, if you think about integrating LLM with logic, then it's clear that you have to adjust embeddings to adapt them to logic construct, because if you're only based on words and different things like that, then you won't have these logical construct which are really central to inference. So today we'll have Yuli who will say more about this topic. Okay, if you look at logic and practice, then you can see that you have a lot of knowledge which is in form of unary and binary relation, like what we saw already. So that you state facts like the ISC 9000 is a course, Roger is a student, Canada is a country, otherwise a city. So unary relation is facts about a single entity. And binary relation, which are relation between two things, like between Roger and ISC 9000 or between Ottawa and Canada, Ottawa is the capital of Canada. You have a lot of facts which are represented and these kind of things. And this is formalized to what's called nowadays knowledge graph. Maybe a good example of that is Wikidata, which is the facts which are used behind Wikipedia. So facts like on capitals of countries and things like that. And when you add to that actions like the one that we saw that gives some constraint on the things, then usually you will speak about an ontology. So an ontology is not only the knowledge graph, like the relationship between things, but also these actions which constrain things. And this is a much developed approach. And the World Wide Web Consortium had developed a lot of technology to support that. So to the encoding, how this is encoded in a file, how constraints are represented, and all these things have been pretty much developed. So you have a lot of technology based on that. And the question of the dividing an ontology, so if you want to apply that to some specific topic, then it's clear that you must make some sort of engineering effort to build up this thing. What are the kind of typical applications? So you can have application like the case with the capitals or continents or things like that in geography. You have a lot of application in biomedical data because you have some molecule, you have illness, you have organs, and you have relationship between all those things. And you want this knowledge to be some sort in a machine processable form so that you are able to do these inference in some automatic way. And really an important fact is that you want it to be interoperable because then you'll have some facts, maybe some biomedical fact coming from one place, coming from another place. You want to put that all together to use that in knowledge bases and application in some sort of uniform way. And on the engineering side is that the quality of the data and also correctly formalizing the implicit semantic of the data, that's really the central thing that you have to build up these things. So it's an engineering effort. And that combine and coordinate many people, so you have domain expert who can really explain the meaning of these things, but also ontologists who know the technologies and how you can formally, and they have to work together to devise these ontology. So this question about how you coordinate this work, how you create the best process to create these ontology and how to decompose the different tasks that had been being done. And this afternoon, then John will tell us more about these questions. And finally, the ontology is a formal artifact. So dividing an ontology is like similar to writing a computer program, but there's a very specific difference is that the computer program is a sequence of instruction that will be executed by the computer, but the ontology is it's more like it's a set of declarative statements. So it's constraints that represent knowledge. So that brings really specific difficulties and challenges to make to correctly divide these ontology. And you can ask yourself here again, so could LLM be leveraged for this stack? So to really keep these guarantee provided by logic-based framework, but help in devising this formalization correctly. And Dean will tell us some things about that this afternoon. Okay, So I think this is pretty much all for me. So we'll have a nice day around logic and ontology, and then 2 other days this week about computer application.